Hello, I am Geoffrey Mendiola and this is my Lab 3 video blog. I will be discussing the adder and the subtractor. So first, we will tackle the half adder. And this is the truth table for the half adder. So 0 plus 0 equals 0 sum 0 carry, 0 plus 1 is 1 sum 0 carry, 1 plus 0 is 1 sum 0 carry, and 1 plus 1 is 1 carry. So this is the K-maps from the truth table, and from the K-maps we can get the expression for the output sum and the output carry. So for the sum, we followed A naught ended with B, and it is ORed with A ended with B naught. And then with the carry, it is A ended with B. And this is the half adder when it's using a component rather than basic logic gates. So here we can see the half adder, and here I used a XOR because the output for sum is the same as XOR. And then we also have the half subtractor, and this is the truth table for the half subtractor, and from that we get these K-maps, and from these K-maps we get the expression A naught ended with B, and it is ORed with A ended with B naught, same as the half adder. And for the borrow, it's A naught ended with B, and here is the only difference to the half adder. And here's what it looks like when we use the subtractor component. So we can see that here in here. So it just works the same. When we look at the truth table of this, it's the same here, 0, 1, 1. And then now we will go to the full adder. So for the full adder, this is the truth table for the full adder, and from this truth table we will get these K-maps for the sum and for the carry. And here is the equation that we will get from the K-maps. So A naught ended with B naught, and carry in ORed with A naught ended with B and ended with C in naught, and it is ORed with A ended with B naught and C in naught, and it is ORed with A ended with B ended with C in. And for the carry, it is B ended with C in, ORed with A ended with C in, and ORed with A ended with B. So I will be creating a full adder. So a technique in creating the full adder is we can use the half adders. So following this form, I will just get the half adder there. And then this will be the input here. And then we will have another input, which is Cin. And then this will go into a OR gate. And there we have the full adder. To check if we got it right, we can compare its truth table here to the one here. So there, if we compare it side by side, we can see that it is equivalent to each other. 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, and 1, 1. And now we will go to full adder using a component. So here in arithmetic, we have an adder. And so in order for us to use it, so for example, I will make a 2-bit by 2-bit. So the data bits have to be 2. And so this, I'll also make this 2. Then connect it. Then for the output, you can also use a pin. We set it output, yes. Then connect it. And then for the carry, we will connect it here. So to test, we can test. So 1 plus 1 is equal to 2. This is 2 in binary, so and continue to check. So 3 plus 1 is 4, and this is a carry out. So now we will be going to the full subtractor. So on the full subtractor, this is the truth table for the full subtractor. And from that, if we get the K-maps of the difference and the borrow, we can get the expression A naught ended with B naught ended with B in, ORed with A naught ended with B ended with borrow in naught, ORed with A ended with B naught ended with borrow in naught, and ORed with A ended with B and ended with borrow in. And for the borrow out, we get the expression A naught ended with borrow in, ORed with A naught ended with B, ORed with B ended with borrow in. So just like in the full adder, we can use this technique in creating the full subtractor. We can make use of our half subtractor. So I will do that now. Wait, please. Begin. Then connect this to an OR gate. So let's check. And so to check, we analyze the circuit and we look at the table. So for this table, we can check here. So we get the difference of A minus B in is 0 with borrow 0, and 0, 0, 1 has a difference of 1 and borrow 1. 0, 1, 0 has a difference of 1 with borrow 1. 0, 1, 1 has a difference of 0, borrowed 1, and 1, 0, 0 has a difference of 1, borrow 0, and 1, 0, 1 has a difference of 0, borrow 0, and 1, 1, 0 also has a difference of 0, borrow 0, and 1, 1, and 1 has a difference of 1, borrowed 1. So it is equivalent to the full subtractor. And then we can also make a full subtractor using the subtractor component. So I will make an example of a 2-bit subtractor. So there. So the component bits have to match the input bits, which is 2 bits. And then that's the carry out. And for the output, to set this to output. Yes. Now it will display the output. So to test, we have 1 minus 0, 1 minus 0, 0 is 0, 1, and 0, 1 minus 0, 1 is 0, 0, and 1, 1 minus 0, 1 is 1, 0. So now if here's the borrow. So now if we want to make a ripple adder or a ripple subtractor, we just have to cascade these with more sets of subtractors and adders. And that's the adder and subtractor.